Hello everyone, I'm Qian. Today I will introduce our work entitled PrimeNet, a framework for common sense knowledge representation and reasoning based on conceptual primitives. First, let me introduce the background of this work. Common sense knowledge acquisition and representation is a core topic in artificial intelligence, which is important for building human-like AI systems. However, existing common sense knowledge bases organize facts in an isolated manner, like bag-of facts, lacking the cognitive level connections that humans commonly possess. In fact, humans are able to function well in most real-world situations using a small set of concepts, as opposed to dealing with an exhaustive list of specific entities. As shown in Figure 1, humans describe common sense knowledge like hammer can be used to drive nails into wood. We commonly describe this common sense knowledge using the concepts such as hammer, nail, and wood. We do not use the overly specific terms like engineering hammer, rubber hammer, or too abstract terms like tool. For estimated or effective vocabulary, the number of words that people need in order to understand 95% of everyday text is around 3,000 words. And the average size of American freshman college students' vocabulary has been estimated at about 12,000 words. This underscores that human ability to distill extensive information into manageable concepts, facilitating a more streamlined expression and understanding of daily experience. In fact, human cognition relies on a small set of fundamental and innate building blocks called primitives. Based on the conceptual dependency theory, primitives serve as elemental units of information and actions like color, shape, size, increase and decrease, and form the foundation for humans to make generalization, inference, prediction, as well as reasoning and understanding in a wide range of real-world situations. So, inspired by conceptual primitives, in this work, we propose a new framework for common sense knowledge representation and reasoning based on conceptual primitives, named PrimeNet. The PrimeNet framework consists of 3 layers, as shown in Figure 2. The primitive layer comprises fundamental and universal elements that act as the building blocks of cognition. The concept layer is commonly used mental representations of categories or classes of objects, ideas, or events that share common features. The entity layer represents specific instances or examples of concepts. To build PrimeNet, we began by gathering extensive common sense knowledge from diverse sources and integrate it to form a raw knowledge graph. Unlike a simple aggregation of facts, we adopt a gradual expansion approach. Initially, we contrast the graph with co-concepts and relation types, systematically expanding it by adding more specific entities and intercropping diverse relation types. Figure 3 shows a PrimeNet preliminary knowledge graph. The initial knowledge graph collects all natural language relationships between concepts found in the training data. After several rounds of normalization, the final PrimeNet graph only leverages 34 relationships. In the next stage, we establish the conceptual layer of PrimeNet by assessing the abstractness of all nodes using a new score function tailored for conceptualization. Moreover, we design an LLM-based primitive detection method to build the primitive layer of PrimeNet. Then we manually check the primitives, refine the hierarchy structures, and generate explanation of primitives. For example, the active is defined as change of status from on to off. In Table 1, we provide some examples of verb primitives in PrimeNet. Given the input stream, we show the detected verb primitives and its primitive level representation and explanation. Then we introduce the background of using conceptual primitives for building knowledge base. In linguistics and cognitive science, conceptual primitive commonly refers to a basic concept or idea that serves as a foundation or for understanding more complex concepts. In modern large-scale knowledge base, there are some works to use primitives to contrast a knowledge base. For example, Sentic 8 is designed to build a knowledge base in a way intercropping co-primitives based on conceptual dependency theory and linking a vast amount of facts. In this work, we will focus on building the Commonsense knowledge base based on conceptual primitives. For the overall framework to build PrimeNet, there are 3 modules. Module 1 is knowledge graph construction. It is to build a huge knowledge graph to represent Commonsense knowledge. Module 2 is to do concept detection and build the concept layer of PrimeNet. Module 3 is to do primitive discovery to construct the primitive layer of PrimeNet. Then we will introduce the knowledge graph construction. This is a challenging step for building a huge Commonsense knowledge base, as it involves a vast amount of facts expressed in different forms. According to the theory of cognitive development, human cognitive development occurs in stages. This inspired us to design a gradual expansion strategy to build our knowledge base, instead of directly merging diverse sources. In the first step, we collect high-quality Commonsense knowledge from diverse sources such as WordNet, DBpedia, ConceptNet. The sources and their examples are summarized in Table 2. The next step, we integrate the knowledge into one graph. The collected knowledge in Step 1 is from different sources in different formats. We first deal with individual sources and then build the mappings between different sources using existing high-quality mappings as well as lexical level and semantic level matching methods. Table 3 summarizes the details of knowledge integration for individual sources and mappings between sources. In Step 3, we contrast the graph in gradual expansion. Figure 5 shows how we contrast the graph. First, we start with WordNet. We first construct a basic graph with co-words and relations from WordNet and ConceptNet. Table 4 summarizes the co-relations used in the co-graph. Then we add instances of knowledge from DBpedia and Wikipedia into this graph. Next, diverse types of knowledge from other knowledge bases are intercropped into the graph of PrimeNet. After constructing the knowledge graph, we design functions for exploring the graph. Table 5 summarizes the designed functions and their input, output, and description. These functions are able to explore the structure of PrimeNet, explore Commonsense knowledge for a specific concept, and integrate new knowledge into PrimeNet. Then, to build the concept layer of PrimeNet, we conduct concept detection to identify concepts that represent categories or classes of objects, ideas, or events based on shared features. An intuitive approach is to use its relation to build mappings between concepts and their entities. For example, corgi is a dog. Dog can be used as a concept of corgi. However, it is not always accurate. For example, animal, dog, and corgi, all these words have specific entities. However, only animal and dog are widely used as concepts in human daily reasoning. Corgi is too specific. As such, the core component in this step is to measure the abstractiveness of a term. If the word is too specific, they should not be used as a concept. Existing methods are mainly bottom-up measure using ProBase. It is a large-scale probabilistic knowledge base. It organizes a huge number of its relationships. Existing methods use the leaf nodes as the most specific terms, and they are considered as the first level. The levels of other nodes are defined as the length of the longest path from the leaf node to itself. So this method is not accurate, as shown in Figure 6. The cohorts from WordNet are expected to have higher scores in different types of abstractiveness measures. However, existing methods cannot tell them from normal terms. In our method, we design a new abstractiveness measure to conduct concept detection, as shown in definition 5. Previous methods exploit a bottom-up approach to measure abstractiveness. The leaf nodes are set at level 1, and the scores of other nodes are computed based on these leaf nodes. Different from this method, we start from co-concepts and use a set of co-concepts to infer the abstractiveness of other nodes, which is more accurate. Figure 7 shows top 50 examples scored by our methods and other score methods. It is observed that our score function is more effective to detect concepts. In our method, the primitive discovery is to identify the most basic and essential element of the word knowledge, which provides a way to represent and organize knowledge in a structured and meaningful manner. The well-designed primitive set can help to produce more accurate and reusable knowledge base. However, creating a good set of primitive is extremely time-consuming and labor-intensive. In our method, we first apply an automatically method to build a primitive set. The basic idea entails clustering concepts that share similar functions at the cognitive level, then labeling the most representative concept in each cluster as a conceptual primitive. Then we design a large language model-based method to refine the primitive set. Based on the clustering concepts, the first language model is used to detect the primitive of the given set of concepts. The second large language model is to judge whether the selected primitive is good or not to be used as the primitive of the given concept set. After the PrimeNet construction, we conduct extensive experiments to verify the quality of PrimeNet. We compare PrimeNet with other widely used knowledge base in terms of coverage, accuracy, and efficiency. First, we conduct the statistic analysis of PrimeNet with other knowledge bases. The human evaluation is used to test the accuracy of knowledge stored in PrimeNet. The performance is shown in Figure 6. It is observed that our PrimeNet has a higher accept rate compared with other knowledge bases. Then we use different knowledge bases on the semantic similarity task to verify their effectiveness. They are used as external knowledge to improve the pre-trained word embeddings. After the knowledge integration, the trained word embeddings are used on semantic analysis task. The enhanced performance are used as an indicator of quality of knowledge bases. The performances are shown in Table 7. It is observed that the PrimeNet achieved the best performance, showing its effectiveness in enhancing the semantic representation. Another task is neuro-symbolic common-sense reasoning. We use different common-sense knowledge bases to enhance the neural networks for the common-sense question-answering tasks. The performances are shown in Table 8. It is observed that the robota-based models with external knowledge from PrimeNet achieved the best performance, showing the effectiveness of PrimeNet. Then we conduct case study on PrimeNet. Figure 9 shows the example of hierarchical structure of primitives in PrimeNet. For the top layer, it is the logic definition of generate. Then we found that the primitives like generate, create, active, birth are located at different layers in the primitive structures. We have also performed experiments on affordance by testing how PrimeNet is able to model human-object interactions in different scenarios, such as how to identify and use liquid containers, and in different modalities such as speech processing and computer vision. We also carried out preliminary experiments on how PrimeNet can represent and handle different types of domain-specific knowledge, such as safety commonsense knowledge. To conclude this work, we designed a new commonsense knowledge base named PrimeNet based on conceptual primitives. Our contributions are summarized as follows. First, we design a new representation framework for commonsense knowledge based on conceptual primitives with a 3-layer structure: primitive layer, concept layer, and entity layer. Second, we build a new commonsense knowledge base named PrimeNet based on the designed multi-layer structure. Third, we designed a new concept detection method for PrimeNet to build the concept layer. The last one is primitive detection method for PrimeNet, which is used to build the primitive layer. PrimeNet are available on Sentic's GitHub, and PrimeNet is also available as an API for warp non-generalization and as a set of embeddings for aspect-based assessment analyses available in 80 different languages. The useful links are also provided here. That's all. Thank you.